Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. As I mentioned from my introduction, I also mentioned that we're also going to discuss the decimation in time domain and also decimation in frequency domain. So what does it mean? So suppose if we have values, discrete time values or discrete signals, and they are numbered, number of computations, and you want to reorder them or rearrange them. So you rearrange them according to whether they are even or odd. So the number of even values or odd numbers are going to be rearranged or reorganized or reorder. So the ordering of these numbers is what we call, firstly is going to be the decimation in time domain. I mean, that is DIT. Decimation in time domain. So that is the combination of even and odd numbers. That is the first thing. But if you again rearrange for the second time, mainly focusing on the frequency domain, then it's going to be the decimation in frequency domain. So there are two things different here. Just listen to me carefully. First of all, we arrange the even numbers and odd numbers in their time domain, which is DIT, which is decimation in time. And also, for the second time, we are going to rearrange these even numbers and odd numbers in the frequency domain, which is going to be DIF, which is decimation in frequency domain. So this is what we are going to discuss for the next point that we are going to come up in explaining one of the points of this chapter. So let us begin with what we have said, that we are going to the decimation in time of first Fourier transform, first Fourier transform algorithm or domain. So okay, we put it algorithm. This is what we are used to. So decimation in time domain, or which is abbreviated as DIT, FFT algorithm. So we just begin with this one. So as I said, if you have, for example, the number of samples that you want to compute, remember we are still focusing on two properties of DFT, which can be enhanced, of course, using the FFT. Remember, we used one of the n squared complex multiplication, of course, but also we have n into n minus 1, which is complex addition, if you can recall very well. So these are the former computation that we used in a DFT. So the first Fourier transform tries to make this one faster by using the periodicity properties. Instead of using this multiple property or complex additional property, the first Fourier transform uses what we call periodicity and symmetrical or symmetric property to overcome this. And these are nothing that they are the ones that we discussed last time, which are where we convert the big Wn and k, which is e power j2 pi nk over n in this case. This is what we call the periodicity, and it is used to abandon the big or huge computational numbers that we are facing in DFT. So these are what we are going to use. Instead of using these ones, we are going to use this formula, the slow out. And remember, we discussed this one even in the previous chapter, where we said that the periodicity, we use these ones, and this is nothing that you can even pull out depending to which value you have been given. Suppose if you are given cosines and sine value in trigonometry, remember, then you can easily convert using this value. You can also be given in any of these notations, you can easily get this one. So in dissemination, in time domain is going to use this algorithm, whereby we use these properties, these two properties, to overcome the problem. And if you can recall very well, last time we said the symmetric and periodic properties we are having. For example, if you have a circle having its point from their origin, having their point in origin, it can be clockwise or anti-clockwise direction. But in this case, for example, you can recall very well where we stipulated and saying -1 point, and there J, J. We talked about J in this case, and we talked about 1. So this is -1. This is 1. Remember, these are real values, or the value of positive number. This is imaginary number in this case. So we are having such a kind of points from their origin. So you can have point here, point here, point here, and 4 quadrum. So we have 4 portions of a cycle, whereby you can arrange according to any values. So to know the values here, this is what we get. So the number of nk can be computed. It can be 0 point something on the other side. Can be, so you arrange them to any point here, be it in the imaginary value or the real or axis, the y x-axis values. So this is what we mean. So suppose if you have any number, take any number, for example, of given this value, you can compute this. For example, you can have W big N, for example, of K, that is a shift theorem that we talked about, of N over 2, which is, if you compute it, you are going to have another equivalent of this value on the counterclockwise direction. But also you can have another big N of K plus N, K plus big N, and you get this negative value is okay. This is K because there is no N, and this is going to be big W N of K. This is the corresponding. So the shifting theorem can shift from the left. Remember, if you are putting this plus, it is showing to it is going to be the other way around. So you take it to the right-hand side, and then it becomes negative or depending on how you have shifted it. So these are the symmetric property and periodic property. So the periodic property is going to be this one, but symmetric is going to be the first one. So they are arranged according to, and remember they are based on their cycles, so they are periodical. So the first quadrature here goes this one, the second quadrature, and so on and so forth. So this is what we are going to use using this FFT algorithm. We are trying to ignore the first n squared complex multiplication and n into n minus 1, which is additional property, to shift to these elements. And you will see its usefulness when it comes to calculating the radix, as I mentioned in my introduction, the radix 2, the radix 4, what, and so on and so forth. So having your value, for example, we are still continuing in the DIT, which is decimation in time domain of FFT algorithm here. Suppose if you have any value, in this case, of Wn, this is what we are going to use. Remember, we said it's going to be e power j2 pi n, okay, over big N. So no. In this case, if I don't put any k, this is not given. So it's going to be e power j2 pi only, because nk is not mentioned here, over big N. And this value has the two relationships with the former ones. Suppose if we have number one, if we have, for example, Wn raised with two values, for example, in this case. So remember, it's going to be the continuation of the other side. It's going to be e power j2 pi and then times 2. Of course, we are going to bring this one over n into 2. So in this case. And this one also can have, for example, you can even interpret it, for example, it can have a certain relationship in this case, whereby e j2 pi can be divided, for example, n over 2 in this case. Because if you want, you can take it down, and this is nothing but it can be w n over 2. That one also is also can also be common. These are the two relationships. That is the relationship number one. The relationship number 2 in this case is going to be, for example, suppose if we have a shift theorem whereby we have Wn shifted by k times, so it's a k plus n over 2 in this case. What will come out? What is the relationship do we explain? So according to this value here, we shall have j2 pi. Then in this case, it's going to be, it can also be k plus n into 2 in this case. But remember, there is another n in this case. So, and this can bring out, for example, it's also common that j2 pi over n into, for example, if we want to take them out, for example, you can have e power j pi. These are the very common relationship in terms of shift theorem, if you can recall very well where we wrote this into k in this side. So This one also is very useful once you have this one. This one can be delivered depending to how many positive numbers and variable. These two relationships are very common in terms of the decimation in. Remember, decimation is trying to divide the big number of computations using the even values. So that's why you see, so first of all, you say the even values with their corresponding odd values, where we shall obtain without a division by k. So you can see this side there is no division of 2, but before there were 2. So we are trying to combine the even values with odd values in this case, and that's why, and that one corresponds what is the explanation of DIT or DIF. So these are the very, very useful relationships. We are going to also continue from this relationship, building on these relationships. We can come up with another new thing. This is a continuation of what we saw. So we're still continuing on DIT, which is a decimation in time domain using FFT or Fourier, fast Fourier transform algorithm. Remember, if we have talked about the even and odd samples that we are supposed to break them and just put them in a proper way. So talking on even, suppose if we have for example, let the value be our n be equal to 2r, for example. 2r can be 2k, can be 2t, can be anything else. So using these values, for example, using the symmetric value and the periodicity property, if you have you are a special case of n times, and you want to get the integer of power of 2, for example, having big N, which is equal to 2r, as I have mentioned. You can also put it in a separate way by having x of n into suppose if you have 2 signals and you want to get the ratio of the 2 sequences, then you can also divide it and just be n over 2, for example. The length, you can just reduce it into a half, for example. And if the even indexed or even sequences for the first time is going to be sampled for the first time, and the odd sequences are going to be sampled the second time, then you can either get the first sample as x of k in this time. Remember, we are still using our formula, which is n minus 0, n minus 1, small x of n, then power e. In this case, we are going to pull out j into 2 pi, then over n into nk. In this case, it's the same equation that we used in this case. So here you can have, which is going to be summation of n is equal to 0 of n minus 1 x of n into e 2 pi over n times nk, then plus another value which is going to be the odd value in this case. So the odd value is going to also to be the same case, whereby this is, for example, the even the n even. In this case, they don't care about putting the n odd. In this case, they don't even put n at 0. Then n minus 1. Then x of e or n. The same thing as we have pulled out the 2 pi over n, then nk, or kn in this case. So there is this one, the main formula, but you can divide them and just mention that one is odd, another one is even in this case. So sampling this in this case is going to be easier for you to know which portion has been in even numbers or which portions are going to be the odd numbers. So suppose now we have we are trying to explain our even numbers and odd numbers in case just substituting it in our formula. Remember where we have, for example, our formula. Remember we have our formula like this, which is the summation of n is equal to 0, big N, then small x of n in this case, then power e into negative j 2 pi n k over n, which is also, if we substitute the wn in this case, we can have our summation, which is n is equal to 0 of n minus 1 x of n into w n k in this case. Let, for example, see, for even values, we are going to have n, which is equal to 2r, as I mentioned from the beginning. For even numbers, or even samples in this case, and also n is equal to 2r plus 1 for odd numbers in this case. So if we can substitute it there, then it's so obvious. We can get big X of k in this case, having in this case we are going to have the n equal to 0 of the big N that we have into, for example, over 2 minus 1 x of n, which is x of n in this case is going to be 2r 2r for even numbers. Okay, we are here. Then n into 2r. This is for even numbers. Then plus summation of this is odd into n over, of course, it's going to remain the same, over 2 minus 1 x into n numbers, which is 2r plus 1 w big N into 2r plus 1. But remember, if you have to include nk in this case, you can put it the k values. For example, n is this one, then you put k for everyone. Remember, this is small n and this is small n. For both values of even numbers and odd numbers. So you can substitute them and just put, for example, and this is, in this case, it is R which begins from 0, not N. So R begins from 0. So we are putting it in terms of R. So combining them, for example, we can have the values, for example, in this case. It's quite normal, so it is the same. So it's going to be, in general, it's going to be x of k, which is equal to summation of R is equal to 0, big N 2 minus 1. Remember, it has been N minus 1, but we said it's going to, N is going to be 2R. So x of 2R times big N into 2R k, in this case, plus what you have got, this value. So it's going to be the same. So, and if we substitute, for example, remember where n here is equal to e power j 2 pi, 2 pi, so over n in this case. So it is nothing new there. It is what we have been using. It is the same case that we have been using. We are only substituting the values of the n, small n, where it can be 2r for the even values, and n for odd values, which is 2r plus 1. As simple as that. The rest is our formula, which can be written in the same case. So you can see, suppose if we have W big N of 2, as we mentioned from the beginning, so the 2 is going to be the multiple of k value. That is, this is the value of k, where k can be ranging from 0 up to n minus 1. So n minus 1. So this is very common, substituting our values. It is easier that you can substitute in any big number. So you take, finally, the even part. The even part is going to be one function on itself, which is g of k, for example, then plus another portion which is comprising of wn for another element, function of k in this side. So we have two portions, which one is the odd, the even one, and the odd one. So if you substitute any value, that one doesn't make any big difference. The only thing is how you have defined your odd numbers and even numbers. So we have two functions, g of k and h of k. And h of k. So the rest is going to be multiplied by w or wnk. And this is the 2-point DFT of each sequence. So there are going to be 2 points. 1 point, then second point. So that's what we explained in the 2 points. So we are still on DIT, which is decimation in time domain using Fourier transform algorithm. So that's what we are discussing. So in the next sessions, where we'll be just hearing some of the 2-point DFT calculations, it is nothing but this one. But also the 2 points is going to be n over 2, in this case, point. So they can say, calculate, given a number, and they say, calculate the n over 2 points, a DFT of each sequence. So you can analyze the first sequence, then the second sequence, then you get your n over 2 point solutions. To summarize on what we have seen for FFT algorithm, first of all, we have seen that if we want to create even numbers and odd numbers, you can, in terms of small n, you can say, for example, 2r, which is even numbers, then 2r plus 1, which is even numbers. That is one thing that we have realized here. We also know that when putting substituting on the where there is n minus 1, it becomes n over 2 minus 1. If you substitute all those values, that is number one. Also, second point that you have to make. We also have to come up with the end, the coefficient that you are going to multiply on your equation, which is Wn. It can be Wn. And for DFT, DFT algorithm using FFT, remember, if it is a Wn, then it's going to be Wn over 2 for n divided by n over 2 point algorithm. So there are three main points here that we have to make. First of all, you have to break them into even numbers and odd numbers. And remember, for the even numbers, we are going to consider small n as 2r. Then the second portion is going to be odd values, which is going to be 2n, and small n is going to be 2r plus 1. Then we also have to remember that when applying the n over 2 point, Wn is going to be Wn over 2, or for n over 2 point algorithm. So those are the main, it's like a summary of FFT algorithm in this